Hey Bulldogs, this is Mrs. McInnes. We are continuing our study of calculus. We are in section 2.2, the limit of a function. And I am on page 4 of your notes packet. Okay, so our objective today is going to be to determine the limits of a function given either a graph or an equation. And we're going to learn an approximating method today using graphs on the calculator. We will learn how to evaluate limits algebraically in the next section in another video. All right, so first we're looking at the definition of a limit. And you would read this out loud as the limit of f of x as x approaches a equals L. And in general, when you are looking at a function, we're saying as x gets closer to some certain number, what is the y value approaching? That's what L represents. And then it says if we can make the values of f of x arbitrarily close to L as we like by taking x to be sufficiently close to a on either side of a but not equal to a. And that is what might be a little bit new for you in terms of the idea of a limit. We don't care what happens at a, we care what happens as we get closer to a. So there are 3 diagrams on here to illustrate 3 different examples of a limit. So on this first example A, we're finding the limit of f of x as x approaches a. And so as x gets closer and closer to a from either side, what is happening on our graph? Well, if I started over here and then I moved closer and closer and closer, or if I came from this direction, my y value is getting closer and closer to L. So on this first example, we actually happen to have a point at that limit. Look at the second example. There's actually an open circle. It's kind of hard to see here, so I'm going to make that bigger. There is an open circle. However, the limit of f of x as x approaches a on this one, so as we get closer and closer to a, we're looking at what happens around a, not at a. Because a has a point, it's just defined elsewhere. I don't care about that point. I care about what my y values are approaching, and they are approaching L. And then the last example is a problem where we have an undefined point on the graph, a hole. We'll later learn that to be a removable discontinuity. And we don't have any other point as we did in the second example. But we're finding the limit of f of x as x approaches a. And so as x gets closer and closer to a along my curve, my y value is getting closer and closer to L, regardless of which side you're coming from. Okay, so this example down below, for the equation f of x equals x cubed, that's the same example we looked at in the previous section in 2.1. As x approaches 2, what is f of x approaching? So another way to write this using the limit notation is the limit of the function x cubed as x approaches 2. So if we were to just draw a sketch of this, we know a cubed function looks something like that. And at 2, let's look at where we're at. We've got a point at 1, 1 right here, and then at 2, 8 up here. So my question is, as we get closer and closer to 2 from either side, what is happening to our y value? So I'm going to get closer and closer and closer to 2, whether I'm coming from this side or whether I'm coming from this side. Closer and closer I get to 2, I know my y value is getting closer and closer to 8. So when we have a nice smooth curve, like this example of a polynomial, the point 2, 8 is actually the exact x value we're focusing on for our limit and the exact y value. But that's not always the case. Very often we're evaluating limits where there is a point missing, like one of the 2 examples up here. So the answer to this problem would be as x approaches 2, y is approaching 8. All right, so let's take a look at example number 1. Guess the value of the limit as x approaches 1 of x minus 1 over x squared minus 1. Now, on the previous example, the easiest way to guess this limit is we could just plug 2 into our function. 2 cubed is 8. Our answer was 8. On this example, if I just tried to plug 1 in, 1 squared is 1 minus 1. I'm getting a 0 on the bottom and a 0 on top. We can't have a 0 on the bottom, which means we need another way to evaluate this. There is something wonky happening at 1. It could be a vertical asymptote, it could be a hole, and we'll learn about finding those algebraically later on in the next section. But for today, we're going to explore this with the graph, with the graphing calculator. So we're going to go ahead and graph this. I'm going to go to my y equals, and just to save us time, I already have this equation in here. Let me go ahead and turn off the visibility of my other equations I have in here, and I only want to see the first one. So you can make sure that only the first one is highlighted. So that's a nice little trick on the calculator so that you can still keep equations in there. And I'm going to just go back to a standard window. So I'm going to start with Zoom 6. And we are looking for what happens as x approaches 1. Now you could sit on the curve, so let's scoot this up a little bit. Let's hit our trace key. And I'm sitting at the point 0, 1. You could move along the curve. So as x gets closer to 1, y is 0.523. And if I go too far, now I'm on the other side of 1, 0.485. Okay, well, maybe I want to get a little bit closer to 1. So we've got 1.06. What if I typed in 1.05? 0.487. What if I got a little bit closer? 1.01. 0.4975. What about 1.001? And so I see it looks like it's getting closer to 0.49975, maybe 0.5. So what's a very helpful tool to use on the calculator is the table, especially when you want to see a pattern of what numbers are approaching. You'll remember we did this yesterday in section 2.1 when we were looking for a tangent of a line tangent to a curve, or the velocity of an object using average velocity. So I'm going to go to my table. So I'm up here at table. So I'm going to hit second table. And I should be able to type in to my X column. If you aren't, right now I can type in the number 5. If you cannot type in, you're going to go to table settings. So table set, and you want your independent variable to be on ask and your dependent variable to be on auto. All right, now I'm going to go back to my table. And I'm just going to start by dropping in 1, but we know that at 1, we have an error on there. And so what I want to do is look at what's happening around 1, because we already knew that we would have an undefined function. So I'm going to pick something like 1.1, 1.01, and I'm just going to get closer and closer and closer. Now, I just did this when I was using the trace function on the graph, but it's very helpful to see this in the table because you can see what the numbers are getting closer and closer to. And even look at 1.0001. It actually hit 0.5, but just so you realize, if you move your cursor over, it's not really 0.5, but the calculator is limited by the number of decimal places it can fit within a column when we're looking at the table view. So it's very close to 0.5. What if I wanted to check it on the other side, which I do? Because in order for a limit to approach a number, it has to approach the same number from both sides. So on the other side of 1 would be 0.9. Whoops. Would be 0.9. If I get a little closer, 0.99, 0.999, 0.9999. And you can see the same exact trend, but the numbers are coming from above 0.5 and getting closer and closer to 0.5. Even if you move your cursor on top of 0.5, it's not really 0.5, it's 0.50025. But I think it's a very safe assumption that from both directions of x equals 1, we are approaching 0.5. And please remember, we will learn how to do this algebraically very soon, as in tomorrow. All right, look at example number 2. Estimate the value of the limit as t approaches 0 of the square root of t squared plus 9 minus 3 all over t squared. All right, so the question is asking us to evaluate this at 0. If I tried to apply what I did earlier, where I could just plug in 2 here and get 2 cubed is 8, if I substitute 0 in here, I get a 0 in the denominator. So it's another graph where we have something wonky happening at 0. So I'm definitely going to graph this one. So I'm going to turn off my first equation, And I'm going to come down here and turn on my next equation. Just to save time, I've already got it typed in. All right, so we're going to go to my graph, and I'm going to take a look at it. And I'm still looking at a standard window. And we're going to look at the behavior around 0. Now right now this is looking like a line. I don't think it's a line, so let's zoom in a little bit. So zoom, option number 2 is zoom in. Well, it still looks like a line right now. Let's hit the trace key and let's type in 0 and see where we're at. And sure enough, I don't have anything at 0. So let's pick something very close like 0.1. So 0.1666, how about 0.01, 0.1666? Okay, so it's looking like maybe that's the number I'm approaching. I'm going to choose to go back to the table again because I love to see that trend of my numbers in table form. So I'm going to start with, obviously I know 0 is going to give me an error. I'm going to go close to 0 like 0.1, 0.01, 0.001, and it definitely looks like it's approaching 0.16 repeating. If I were to sit on one of these, yeah, 0.16 repeating. If I were to try one more, 0.0001, same thing. I'm going to try from the other side. So the other side of 0 would be negative 0.1, negative 0.01, negative 0.001, and I'm seeing the same exact behavior. So this is approaching 0.16 with a 6 repeating on there. And there is something a little weird that happens with this graph, and I gave you a little hint on paper which said try zooming in a lot, but it actually takes a while to hit zoom in, zoom in, zoom in. But what happens if we get so close to 0 here? So what if instead of negative 0.001, I just right away put tons of zeros in here? Uh-oh, we get this weird 0. If you tried a few less zeros, we're getting zeros again. So this is an example of how sometimes the calculator can't truly estimate what a value of a limit is by approximating because of some limitations on the calculator. And what we're doing is we're making this t value so small that t squared is approaching 0. And so square root of 9 is 3, 3 minus 3 is 0. So the calculator is thinking that that numerator is 0, when in fact it's not. It's just a rounding issue. When this is so small, this square root expression seems like it's 0 plus 9 when it's really not. So I just want you to keep it in the back of your mind that using the calculator to find limits is great, but we do have some limitations because the calculator doesn't think. It operates under an algorithm. And so we're sometimes going to have to rely on our algebraic skills to get accurate answers. Okay. There is one more example up here that's just a little strange. So it's the limit as x approaches 0 of sine of pi over x. So I'm going to go to my graph, and I've got this one loaded in here as well. And I'm going to take a look at the graph. And remember, I'm already zoomed in a little bit on this one. Whoa, that's a strange graph. We haven't seen one quite like that before. I thought it was going to start off looking like a sine curve, but we've got some weird things happening in here. And so I'm going to hit my trace key, and I'm going to look at 0, because that's what I'm approaching as x approaches 0. And I'm going to put 0.01, and I'm getting 0, and 0.001, and I'm getting 0, 0.0001. It looks like the limit is 0 here. But I'm going to zoom in a little bit more. And what you're going to find is the more we zoom in, the closer we get to 0, the more that this graph oscillates. It alternates up and down, up and down, up and down. And so as frequently as this limit is 0, this graph is oscillating back and forth just as frequently. Which means that this is another one of those strange graphs where if you use your calculator to evaluate the limit, we do not get a definitive answer. Using the values, it looks like 0. Using the graphs, it looks like it does not exist. And in fact, this function does not have a limit, and we write that as does not exist. Now, am I going to give you a question like this on a test? Absolutely not, but I just want you to see that we cannot always rely on the calculator. We're going to have to rely on our algebra skills. All right, the second definition says if we have a limit as x approaches a, and there's a little minus sign on here, and what that minus sign means is from the left-hand side. So the limit as x approaches a from the left of f of x is equal to L. So we can look at a limit from the left side. We can also look at the limit from the right side. And it would have a little plus sign. It almost looks like in the exponent position, but it's not. This means from the right side. So underneath that, I've got 3 different examples. So the one that's in the middle is the one that was originally in definition 2. So this means the limit from the left side. So as x approaches a from the left side. And then this one over here means from the right side. So what happens if there is no plus sign or minus sign? In order for the limit to exist, it has to approach the same number from both sides. And if it does not approach the same number from both sides, then we would say that the limit does not exist. So what we're going to practice here is just looking at a graph that's already created for us, and we're going to grab limits off of the graph. So look at example A. The limit as x approaches 2 from the left side because of that little minus sign. So as x approaches 2 from the left side, well, I'm approaching from this way. So I want to know what is my y value getting closer to. Just follow that point. Even though there isn't a point at 2, that's okay. We only care about what's happening to the left of 2. And this is approaching the number 3. Next question, the limit as x approaches 2 from the right side. So approaching 2 from the right side or approaching 2 from the right side. And as we get closer and closer and closer, like 2.1, 2.01, this is approaching the number 1. So part C is asking, what is the limit as x approaches 2? And since there's no plus or minus, it means from both sides. Well, is this graph approaching the same number from the left as it is from the right? No, it is not. So we would write that this does not exist. And DNE is an acceptable abbreviation for that. You also know, please ignore this interruption. It's picture day today. Please ignore this announcement.
Again, last name, letter C or D. Thank you.
Thank you. Okay, so we can look at the picture from that, but since we've already found the limit from the left and the limit from the right, those are not the same number, so we know that that limit doesn't exist. Look at example D, the limit as x approaches 5 from the left. So here's 5. So as it approaches from the left, remember, we don't care about the actual point. We only care about as it gets closer to 5. So follow that over, and that looks like it approaches 2. As x approaches 5 from the right side, so I'm coming from this direction, that is also approaching 2. And since it approaches the same number from both the left and the right, the limit as x approaches 5 is 2. Again, doesn't matter what happens at 5, just matters what happens around 5. All right, last part. G of 5. Now this has no limit attached to it. So this is literally saying when x is equal to 5, what is y? This is not a limit. This is just an actual point. So at 5, we are looking for the actual point right here. And so if I follow that over, it doesn't look like it's exactly at 1. Maybe it's at 1.3. That's just a little estimate there. Somewhere between 1 and 2. All right, last thing for today. Infinite limits. So finding the limit as x approaches 0 of 1 over x squared if it exists. So the first thing they want us to do is use the calculator. Now obviously we could try that little trick of plugging 0 in, but I get a 0 in the denominator, so that is not going to work for us. So I'm going to go down here to my very last graph, and I'm going to put 1 over x squared. Actually, I'm going to use my numerator denominator. So 1 over x squared. And I'm going to go to my graph, but I had a very zoomed in window, so I'm going to go back to Zoom 6 for Zoom Standard. And you can look at the graph, or you can also use a table. And you guys know by now I'm a big fan of the table, but if you want to look at the graph at 0, it doesn't exist. But if you get a little closer, 0.1, 0.01, 0.001. What's happening? I'm going to go to my table. 0.1, 0.01. Oh, we already have those in there. 0.001. Folks, this number is getting larger and larger and larger. Why is that getting larger and larger and larger? We have a vertical asymptote here. You'll recall from Algebra 2 and pre-calculus or advanced topics that when you have a 0 in the denominator, one of the occasions that can happen is a vertical asymptote, and that's what is happening here. So, find the limit using the calculator. Oh, let's look at our picture. From the left side and the right side, since there is no specification on one side or the other, it is approaching infinity from both sides. Okay, so what if I asked you to calculate this by hand and I did not allow you to have a calculator? What would we do here? So what we're going to do instead is we're going to try to remember what this function tells us from Algebra 2. So when we have a point on a graph where this is undefined, because when x is equal to 0, this function is undefined, it could either be a vertical asymptote or a hole. You will recall that holes only happen when a factor on the top and bottom cancel. So we're not going to see holes anytime right now. We'll see those later on in the course, in the chapter actually. So what we're looking for right here is it's a vertical asymptote. So the question is, we know that it happens at 0 because that's where my graph is undefined. So I have a vertical asymptote at 0. The question is the graph approaching infinity or is the graph approaching negative infinity from both sides? And I have to test both sides because they did not specify one side or the other. So what we're going to do is pick a number very close to 0. You don't have to go 0.00001. At this point, we just want to see behavior. So I'm just going to go 0.1. And all I really need to know is if I'm getting a positive answer up here or a negative answer down here. Because positive would indicate that my asymptotic behavior of the graph is that it's approaching infinity. Negative answer would tell me it's approaching negative infinity. So when I plug in 0.1 on the positive side, I would get 1 over 0.1 squared. That is definitely going to be a positive number. So that tells me on the right side, this graph is approaching infinity. I also need to test what's happening on the left side. So 1 over negative 0.1 squared. Well, a negative squared still becomes a positive. So this is also approaching positive infinity. So what we've really done here is estimate what's happening on the left side and the right side. So this is a limit as x approaches 0 from the right side because we took a positive value. And then this is the limit as x approaches 0 from the left side because we took a value to the left of 0, which would be a negative. So since both of those answers were positive infinity, then this answer would be positive infinity, just like we found when we looked at the graph itself. Okay, one last example today. We are going to look at same idea, finding what the limits are, but we're going to start by calculating by hand. And so when you look at this graph, again, a nice easy way to try to find what the limit is to plug 3 in, but we're getting a 0 down here. And in fact, I know that this graph is undefined when x minus 3 equals 0 or when x equals 3. We found domain in the last unit in chapter 1. So we know that this graph doesn't exist at 3. Why doesn't it exist? It's either a vertical asymptote or a hole. It's not a hole because no factor is canceling on top and bottom. So it's a vertical asymptote. So if I think about my graph, where does my vertical asymptote happen? At 3. So out here at 3, I have a little vertical asymptote. So I want to know what's happening to the right and to the left. So I'm going to start by finding what's happening to the right. And so the limit as x approaches 3 from the right side. And I'll just put f of x here. So what I'm going to do is plug a number very close to 3, but to the right of it, like 3.1. And on top, I'd have 2 times 3.1. On the bottom, 3.1 minus 3. On the top, I'm getting a positive number. On the bottom, a positive number. Note, I don't even care what the value is. I know the answer is either going to be positive infinity or negative infinity, so I just need the signs of my values. So a positive divided by a positive is a positive. So this graph is going to be going up on the right side. Now, so that means the answer is it's approaching positive infinity. For the second part, I am evaluating the limit as x approaches 3 from the left side. So I'm going to substitute a number in to the left of 3, like 2.9. So 2 times 2.9 over 2.9 minus 3. So on top we have a positive. On the bottom we have a negative. And a positive divided by a negative gives me a negative. So this will equate to a negative infinity. So this graph is actually going down on the left side. If they had asked you to find the limit as x approaches 3 from both sides, this would be does not exist because it is approaching 2 different directions. And then we can check this limit using the calculator. So we've got, actually I'm going to clear out this top one. And let's get rid of this one here. Okay, so we are going to be graphing. I'm going to use that alpha y equals to get a nice little fraction in here. 2x over x minus 3. Whoops. And we are going to go back to a standard window, so zoom 6. And we should expect to see an asymptote at 3 with behavior that changes on either side. And sure enough, there it is. If you hit the trace key, this is approaching negative infinity as x gets closer to 3. And right around 3, it hops from a negative number up to a positive number, and then it comes back down from the other side. Okay, so that is our lesson on limits. I hope you found it helpful. Good luck to you.